So Avogadro's law is a simple gas law that relates the volume of gas to the amount of gas in moles. Amadeo Avogadro lived back in the 1800s. He was the first one to formally state a relationship between volume and amount of gas in moles. What's interesting about gas volumes is that the volume is proportional to the number of particles and not to the mass or anything else. It's just the number of particles. So the gas itself, which gas it is, doesn't matter at all. So Avogadro's law tells us that the volume is proportional to the amount of gas in moles, and that's assuming constant temperature and pressure. And then we can state that in a form similar to the other gas laws as V1 over N1 equals V2 over N2. So instead of counting individual gas molecules, we use moles. Equal volumes of gases have equal numbers of molecules. Which gas it is doesn't matter. That's a very odd thing about gases. If we look at a graph of the volume of a gas versus the number of moles of a gas, the intercept here will be 0, which is very reasonable because if there are no gas molecules, it should occupy 0 volume. So we can do problems like this one. A chemical reaction occurring in a cylinder equipped with a movable piston produces 0.621 moles of a gaseous product. If the cylinder contained 0.120 moles of gas before the reaction and had an initial volume of 2.18 liters, what was its volume after the reaction? Assume constant pressure and temperature and that the initial amount of gas completely reacts. So we can take the same strategy of looking for the numbers and making a table to identify what these things are. So I'll sketch out a table here. And the first number I come to is 0.621 moles. So we have the variables P, V, N, and T. This is going to be N because N is the amount of gas in moles. So we'll call this 1 and 2. And then we next come to 0.120 moles. So that's going to have to go in the same column. 0.120 moles. And the next number is 2.18 liters. Now we do have to consider the words in the problem. 0.12 moles of gas before the reaction. The initial volume is 2.18 liters. So these two quantities are associated with each other. Those are at the same time. That's before the reaction. Now, I put this number of moles in row 2, but that's okay because 1 and 2 don't have to be before and after the change. They're just identifying which things go together. So the 2.18 liters goes with the 0.120 moles. And that's a volume, so I'll call that column V. What we're looking for is the volume after the reaction. This is the amount of gas that was produced, and we're looking for this volume. So it doesn't matter what you label them as long as you get them paired up correctly. So this is V1. So we need an equation that has N's and V's in it, and so that's going to be, I always forget which is on the bottom. I think N's on the bottom? Okay. V1 over N1 equals V2 over N2. So here's another equation with fractions in it. So cross multiply to get rid of the fractions. V1 N2 equals N1 V2. Again, being careful of the 1s and the 2s. And then I'm going to rearrange this equation to solve for V1. So I'm going to divide by N2 to get rid of it over there and do the same thing over here. So now I have my equation. V1 equals N1 V2 over N2. Now I can plug in my numbers. N1 0.621 moles, and that's times volume 2, 2.18 liters. And we'll divide that by N2, 0.120 moles. Check the units cancel out. So volume 1 0.621 times 2.18 divided by 0.120. 11.2815 is what my calculator says. And the unit would be liters. Then I need to always think about significant figures. As is common in these problems, each of these numbers has 3 significant figures. So I'll round my answer to 3 sig figs. 11.3 liters. Is that a reasonable answer? We can assess whether it's reasonable or not by looking at what happened with the moles. We went from 0.12 to 0.621. More gas, should that take up more volume or less volume? More volume. So our volume went up from 2 to 11, so it's reasonable. If you get your 1s and 2s backwards, it'll end up going the opposite direction, and that'll give you a clue. Any questions? These simple gas law problems are very similar. You just have to choose the correct equation. Here's another one. This one involves a little more thinking. A scale model of a blimp rises when it is filled with helium to a volume of 55 cubic decimeters. When 1.1 mole of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant temperature and pressure. Well, we can approach this the same way by just identifying what all these numbers are. So we've got 1 and 2, and the first number is 55 cubic decimeters. So we know that's a volume for a couple of reasons. One is that it says it's a volume. And then we've got 1.10 moles of helium, and then we've got this 26.2 cubic decimeters. Does this 1.1 mole of helium, does that go with 55 or does it go with 26? It goes with the 26. So this is saying that the balloon will float if it has this volume. This is saying we've added 1.1 moles of helium and the volume is this. So those two go together. So I need to put them together on the same line, same row. So this is N, and then this is N1, which we can solve for. The question is, how many more grams of helium need to be added to make it rise? That's not asking for the number of moles of helium when it floats, is it? In our table, we have N1. That's the number of moles of helium that have to be in the balloon, the blimp, in order for it to have this volume and actually float instead of just sitting on the floor. Would that be a useful number to know? Yeah, because we know this is what it is right now, and they're asking how much more do we have to add? So if we know the number of moles when it's floating, and we know the number of moles that we have right now, we could figure out how many more moles we need to add, and we could convert that to grams. So this is a problem where pictures can be helpful. So here's my blimp. It looks like a football, so we'll put a little like a propeller thing on the end there. When it's floating, like it is right now, 55.0 cubic decimeters. Right now, it's sitting on the ground. It's kind of flat. 26.2 cubic decimeters. When we have 1.1 moles of helium, this is the volume. So down here, this is 1.10 moles of helium. And what we want to know is how many more grams do we have to add so it'll float? We can calculate N1. That's the volume up here. N1 is the volume when it's floating. So let's do that. V1, see, I always get that. I don't know. This equation works the same right side up or upside down. This time we're looking for N1. So divide both sides by V2. V2 equals V1 N2, no. Start over. Oh, not that over. Yeah. Can you say Monday? I overslept this morning too. I got up at 10 till 7. And it's like a 45-minute drive, so that's always fun. What am I doing? N1. V1 N2 over V2. Yeah. V1. 26.2 cubic decimeters. Cubic decimeters is a weird unit. We don't use it very much, but that's okay. It can be in here. Yeah, that's V2. Just shoot me now. V2, we want V1. This is why you write stuff down, because it can go south really fast. All it takes is one mix-up and it's wrong. N2. Divided by V2, 26.2 cubic decimeters. So the cubic decimeters are going to cancel out. That's encouraging because N is supposed to be moles. So 55 times 1.1 divided by 26.2. 2.3091 moles. And let's ask ourselves, is that reasonable? We're starting here with 1.1, and the blimp is kind of squishy. And here, where it's floating, it's got more moles of gas, 2.3. The volume's higher, so that's reasonable. That suggests that we probably did our math right here. This is the amount of gas in moles that the blimp needs to have in it to float. This is how much it has in it right now. The question wants to know how much more do we need to add, and then it wants that in grams. So we can figure how much we need to add by just subtracting 2.3091. And we currently have 1.10 moles in there. Now don't do this subtraction longhand on the paper, because it's so easy to make a mistake. Do it on your calculator. I stacked it up like that so we can really see what the sig figs are doing. Because I don't want to round yet, because we're not really done. So we need to add 1.2091 moles of helium, but we want to know the mass of that. I'm going to change to another color because this is going to be confusing in here. 1.2091 moles of helium, and we need to convert to grams. It's the molar mass, something we learned before. 4.003 grams of helium per mole. I get 4.8402 grams. We'd round that to 4.84 grams. So 4.84 grams of helium need to be added to this partially filled blimp so that it will rise. So this is an example of a simple gas law problem involving Avogadro's law, but it requires you to think, okay? I cannot possibly teach you every sort of problem that you could run into. And in Chem 1A, you need to be able to do problems that you've never seen before, provided you have the pieces. So here we have the piece of converting moles to grams, and we have finding moles from volume and initial moles, and then we have this thinking part of figuring out what the problem is saying. Any questions?